But why is it not visible? Oh yeah, of course. Let me make it big. So I'm going to, as I realized, I don't know, from last time, I'm going to revise some statistics because that's behind many of these things. And I also watched some videos on these topics on YouTube. And it seems like people don't want to tell you what's going on, right? Or they assume you know. Maybe you know. So you're only 4 of you today. So it's very bad sample. Do you all know what Fisher information is? Huh? Not really.
I've heard about it.
You heard about it. So I think many of these things, the people who try these. So how do you try something new, right? I mean, after all, many times people don't prove something converges or whatever. They try, but how can you try? You have to have some ideas behind what you try. So in all of these things, the basic information that is behind the policy gradient algorithm kind of ideas is the score function and Fisher information. People know this and they think, oh, okay, let me try something like that, whether it works or not. And this is the empirical basis of why many of these things come to hold. But when they explain you, they only explain you the new and fancy stuff. They don't explain you how it got motivated, right? And that's why when I was trying to talk last time, I think this will be more or less a repeat. Well, not a repeat. I want to do quite something which is not all in the slides, but more than what's on the slide. The idea is why did people come up with this, right? Why is this the gradient of log, blah, blah. Why does this all show up like in this form? How does anybody know? And the basic reason is it's kind of obvious. If you know score function and Fisher information, it's kind of obvious this is what anybody would have tried. Right? Whether it works or not in practice and all that is a different thing. But what will you try? You will try exactly what the policy gradient theorem says you should try. This is exactly what you would try, no matter what. There is no magic in it. So that is what I want to do today. I want to do some background, and maybe next time or the time after, we'll use this in different ways, not just from a neural network point of view, because this is obviously hip today. Everybody wants to use deep neural network in a certain way, in this backpropagation kind of way of computing gradients, but you can use them other ways. People have successfully done that. And we'll try to see some other ways of doing it, maybe in 2 lectures or so. So I think the basic idea is, am I on? Oh, what has happened? Oh, anyways, it's an older version of slides uploaded. Anyways, doesn't matter. I know what I'm going to say anyways. So maybe I don't know if I can change it in the lecture, but I will change it in the files. The basic idea is statistical modeling. Right? We are trying to model something. How does statistical modeling work typically? Typically, statistical modeling works by saying, oh, you have a space of outcomes S, and you have certain probability measures on this space of outcomes. Usually it is parameterized. So I think this is, if my slides were updated, the right ones, that this would say that so usually in statistical modeling you have a space. This is where your outcomes are.
Sorry,
Yeah.
is it recorded?
Sorry, what?
If you do you record the lecture?
Did I not press it?
I don't know. Just wondering. You have to minimize the window.
Yeah, I'm recording the lecture.
Okay, then sorry. Don't want to interrupt you.
No. On this thing, I see it's being recorded.
Okay.
No, that's okay. I mean, it's good that you pay attention to that, because one time I didn't. And by the way, if you are watching the live stream ever and you see something is not working, you don't think it's recorded, you don't think you can hear me or whatever, say something, don't chat. Again, I repeat this. Last time something happened and it was just a comment in the chat which nobody. So let me just say, I think the slides, I will change it a little bit. So you have space of outcomes. This is what statisticians are interested in. And what do they think? So you choose some space of probabilities. So P is some collection of, so P theta is probability, probability measure on S. So it belongs to S, parameterized. So this is standard statistical modeling. And what is the goal? You want to find, so if you collect data, so if now we start taking samples, so now given samples, find the best data that matches the sample. So that is what one calls the likelihood. So you want to find data says that the probability, so phi theta given x equals your data, your sample, is greater than, so this is find theta naught is greater than probability that x equals for all theta. So in statistical modeling, the idea is obvious. You think the probability distribution describes your universe, describes your world of outcomes, and you don't know which probability distribution it is, but there is one. You assume that there is one, right? But you cannot look at all of them at once. So your model is okay. You make some guess like what could be these probability measures, and then you choose something accordingly. So a typical example is let's say distribution of. I mean, I'm repeating things just to make life comfortable. So let's say a distribution of heights among people. What does it assume? What's the standard model for anything like that? What do we assume about heights?
Normally distributed.
Height is normally distributed. So if I want to study height, so I say height is normally distributed. So it's distributed with some some mean and some variance. Right? So what would be my theta in this thing if I don't know the mean and I don't know the variance? So my theta would be this pair of vector. This will be a vector. Oh, sorry. This will be a vector. So it will be two possible parameters that you want to think about, right? So you're in this case, you define for each value of mu and theta the corresponding probability density. So I could say L. So this is a function of this is L theta. This is whatever 1 over 2 part t x each power minus whatever, you know this kind of formula. So this is my all choices of probabilities. It could be any one of these. If I say the height is normally distributed, that means height is given, there is this probability to get height of a person. Now let's say I take all our heights, right? So I don't know, some of you are, so let's collect data for class. So class height is our data. So maybe, I don't know. Is anyone more than 2 meters here? I will put mine. 76, 183, 1. So we collect some data. Right? So given this data, what does a statistician do? A statistician says, okay, this is my sample. What value of mu and what value of sigma squared should I assume given this data? So given this data, it's rather simple calculation. You probably have seen this. Given this data, you can always assume the mu to be 1 over n, the sum of whatever this heights. Okay, so call these heights h1, h2, so on. So this is how you collect your mean. And sigma is, you know what sigma should be. Sigma squared should be this highest minus mu squared by the number of samples, something like that. Maybe I'm mistaken. I don't always remember these little formulas. But you can derive this. You can derive. So of course, this is in high school. What we do is we say this is mean, this is variance. But what a statistician says, this is the model for how height is distributed. What is the best value of mu and theta? So what you do is you take this thing and take partial with mu, set it to 0, take partial with sigma squared, set it to 0, solve to get that formula. Right, so this is how a statistician's way of getting the mean and the variances. Okay, so the height is normally distributed from which you obtain this. So this is exactly what we are also doing. Throughout this policy lecture, we are not doing anything different. And I want you to realize that that is what we are doing too. Okay? That is the purpose of today's talk, to convince you that this is what we are doing. Okay, so let me familiarize you with, so this is this okay? Any questions? You know this, right? More or less, but still, what is it clear to you that this is the same as what we are doing in the policy gradient lecture? Okay, so this is, then I can't give a lecture today, right? Otherwise, I can just say, okay, we are done for today. I don't have anything new to tell you. So basically, what this means is find, where is the problem statement here? Find the best theta for which this probability is highest. This means that you have to optimize something. You have to say what is the optimal value of some L theta, which is the probability x equals your data, putting theta equals theta. Right? So this is typically how one considers a model. And this finding, if you solve this, so theta hat equals argmax theta L theta. So this thing is called, this has a name. If you remember this name, then I will be happy. What do you call this in language of statistics? Right, this is what you're looking for. So there is a name for something that you look for. Generally, that's a rule, right? A rule of thumb is if you want something, you give it a name. This is called the maximum. Okay. And how good is your estimate? It depends on some other things. So this is of course good that you can find it. So in the previous example, if I did that, I will find the maximum likelihood corresponds to certain value of mu and certain value of sigma. But is that good enough? For the Gaussian case, it's good enough because you know more. But here you have to think a little bit about whether this is good enough. Okay, so we are doing the same thing throughout this course, and of course, for the policy gradient kind of thing, we assume smoothness, so you can hide everything. But sometimes you cannot assume smoothness. We'll see examples of that, and then you'll have to come back to actually thinking in this language. So. Actually, now I'm confused because, as I said, I have the old slides uploaded. So let's see what's on them. So as to also keep some sort of consistency with what's out there. Oh, this. So this is now a slide that says, okay, what I am saying, what we talked about in statistical modeling is what we are doing, as I had suggested. Why? Because we are trying to say model. Our goal here is we are given a sequence, we generate a sequence of experience or whatever in the real world, which is the best policy that fits the experience, right? This is what we're trying to do. So a policy is a probability distribution, right? On the space of outcomes. The space of outcomes is a state action sequence, a trajectory of your universe. Okay, or you can think of it in many ways. You can just think of it as on actions, on states, on state actions. There is choice of convenience here. But this is a statistical model situation. All right, so we are looking for the best policy, which is the same thing. We are trying to find the MLE for this model. Okay, so best theta is find the MLE. Is that good? Now it's the one and same thing, right? What you do in statistics is the same thing as what we are doing here. Is that clear? Any questions? Because slowly I'm going to assume more and more. Okay, so I don't think this is too hard, but there are various ways of understanding or finding the maximal likelihood function. And so we saw what we want to find. So we want to find theta hat, which is argmax L theta. But what we know about L theta, so if suppose, so these are all numbers, right? If I take log of numbers, then log is a monotonely increasing function. So if I want to look at argmag of this is the same as right. So finding the maximum of this is the same as finding the maximum of this. Right? And assuming things are smooth in the parameter theta, and you want to find the maximum of this object, what will you do? So this thing is called the log likelihood. And what you do is you will define a function as theta, which is the gradient of log L theta. So usually gradient. So this is what I think the slide says, but now that I've uploaded an older version, I have to be sure. Okay, good. So we are looking at maximizing this. So we are looking for the score function. Right? So we want to find the. So usually, typically, there will be a graph. Let's just say theta is one dimensional, one-dimensional parameter. It can be two-dimensional, whatever, n-dimensional. But let's just look at the situation that this is the theta dimension. This is how you plot L theta. So this is the log graph. Right? And what are we looking for? We're looking for the maximum. Right? And what are we computing? At every theta, we're computing. So this is here the curvature. Sorry, the slope, the gradient of this curve. Okay. This is what you want to say is the score function. The score function is just the gradient of the likelihood graph. So no mathematically deep concept is needed to define it. But it has some properties. It has two interesting properties. One is that its expectations, assuming some regularity conditions, the expectation of the score function is 0. And this is a crucially important property because it allows you to compute the variance of the score function. And the variance is the important property. So how the score functions, the variance of the score function depending on your x, because you can think of this as both in theta and in x, right? So when you convert this, you start thinking of this as something as in theta and x, and it has still variance in x. So the variance of the score function is the Fisher. Okay. So that is going to be an important quantity. Okay. Okay. Oh no, maybe I'll, sorry, before I go to the next slide. I thought this calculation should be on a slide. Okay, so I'll do it, or I'll try to do it. I don't know. Sometimes one doesn't remember all the. So for our purposes, for our purposes of modeling the maximal likelihood policy, so to speak, this is something where you can, if you want, assume your state space, the space of outcomes, the X or S, to be discrete, right? So we say P theta belongs to the probability on the outcome space. The outcome space here is trajectories of the either it's the trajectories of the whatever of the agent in the world, or it's just its current state and action, whatever. You can choose. So these are discrete, actually. We can assume that space is discrete. But we don't have to. For whatever I'm saying, if you don't like the sign of integration, you can replace it with the sign of sum. Because what we are doing is clearly a sum. So this is a space where everything will be a summation, but you can write it also as an integration. So for summation, there is absolutely no problem in what I write here. But when you go from discrete to a non-discrete space X, when you have an integral involved, you have to be more careful. Okay, so my basic claim is that expected value P of S theta is 0. Well, it has to have an X in it. So let me, what is it? So L theta is what? It is this is the probability mass / density. So if you have a mass, which you have a discrete thing, when you have a mass, this is all you'll need is sums in X, right? And when you have density function, you will need an integration in X. Okay? And what do we want to do? We want to say what is, so we have log of L theta, and I take the gradient of that, okay? And I need to integrate this with X over my space. Well, okay, X or S. Let's just call it X. Or all trajectories, I want to sum up over all trajectories. So if I do the gradient of this, what do I get? Oh, sorry, I have to also integrate it with, not just with dx, I have to integrate it with this. I want to integrate it with this measure and not with anything else. Do you see what I did? Is everybody happy with my change? And I made a mistake and I changed it. Just so that not to confuse you. Okay, so I want to take expectation. I don't know what dx is, but this is what the measure, this is the probability that we are interested in. All of these things are probability densities. So these are the probabilities that I'm interested in. I'm not interested in what dx is. I'm interested in something like that. So when I look at this and I do this, I get basically, what do I get? I get so I get integral over x. Now I'm confused. So, d theta of f x theta. So f x. Okay, so sometimes it's good to get confused. So I can cancel these things. This is derivative of log, nothing mysterious, just derivative of log. The interesting thing is, can you interchange the derivation and the integral sign? This is not always possible. That is why you have to be careful when you say the expected value of score is always 0. Only when you could interchange these two things, which if you have a summation, which you have when you have a discrete thing, is always possible. You can always interchange the sum and the expected value. So for our case, it's no problem to interchange these two things, and you'll get this will be then d theta integral of fx theta dx for x. But does not matter what fx theta is. Its integral would be, since this is a probability density, its integral is how much? 100, 200, 1. So this is. But to derive this, you needed to interchange these two things. Remember that, which is always okay in our example, because we are in a discrete form. Okay, so this is the property that one typically has to remember about score. The score functions are nice, and just when this is possible, you can compute its variance by taking a second derivative of this. Taking the derivative, maybe I'll not do the computation, but I'll just hint at it, and I'm sure you can find this computation in any textbook on statistics. But the basic idea is that if you can interchange this gradient and integral, then so I will write down a formula. So the variance of S theta, which is expected value of S theta. This is what can be calculated by simply saying that expected value of S theta we know was 0. So d by d theta, expected value of S theta is 0. And do the calculation inside the integral of the log blah blah blah. You'll get a term. We'll get that this is equal to a formula. This is done in almost any textbook, so I don't want to repeat this. But it's a straightforward calculation, just like the one before, using the properties of log, nothing more. Okay, and that formula I will show you for your view, because the end result has a meaning. End result has a meaning, and we should see it. This is how you'll get that formula. Okay, so let's have a look at it. All right, so now that we know what the score function is the gradient of the log likelihood curve. Gradient of the log likelihood. And since it's the gradient, you want to compute its variance after integrating with x. Okay. So expected value of S theta transpose. Okay. And that turns out to be what's called the Fisher information. And it's given by this formula, which I hope is visible, because I can see it on there. Do you see a formula? No, am I on the wrong page? Sorry, I didn't even know that I was on the wrong page, and I thought there is no formula there, which was right. Now there is a formula. And the formula is pretty much, as I said, do this computation, expand this as log L theta and just use the derivation of log. Nothing exciting. Nothing very exciting happens. Just do it and you get it. Right? So this is the formula. The formula is interesting. The formula looks like the formula for a. What does this formula remind you? When you just forget about how it came from, what does it remind you? Nobody did mathematics here. Yeah, I actually only teach that. So for me, I'm a geometer by training. So for me, this is what I would think as soon as you show me this formula. Oh, this is curvature. This is curvature. And it is indeed the curvature of a certain graph. And what happens about the curvature? So forget about all these terminology and all that. If I give you two Gaussians, okay, this is one, or well, it's my drawing of a Gaussian, okay? I know it's not. Can you believe it's a Gaussian for now? Okay, and I give you another one. This is again my drawing of a Gaussian. So this is the mean. Which of the two means you will be more happy with? The one on the left or the one on the right? Huh? Which is better to get? It's better to get this Gaussian, or is it better to get that Gaussian? The left one. Why?
The variance is smaller, so the mean is more information.
Yeah, the variance is smaller, so there is very, when you know the mean, you really know something. There is information in the mean. But if you look at this graph, well, let me hope that I can someday draw this nicely, but for now you'll have to survive with this. If you look at this graph, what is the difference, geometrical difference between these two graphs? At the point here, which one of the two has a higher curvature? Do you remember what curvature is? Let me just.
The last one.
Yeah, the curvature is how small. Bigger curvature means you can approximate the point with a smaller circle, and smaller curvature means you can approximate this by a bigger circle. Right? The curvature is by definition 1 over r of the circle that you can approximate your curve with. Okay? So this has more curvature, and that's why it has more information. That has less curvature, and that has less information. And this is typically what you should always expect. More curvature in any sort of thing means less variance. Less curvature means high variance. So there is a reason why one thinks of this quantity whenever one wants to think about reducing variance. You want to increase this quantity to reduce variance in all your applications. Right? So this is typically the intuition, at least, behind it. The formulas are okay. So if I had specialized this to one dimension, the formula would basically be let me be sure what I have. I would want to write the same kind of formula. Okay, that's how I wrote it. So if I had written it if theta was one dimension, so theta is one dimension, so just one parameter, then I theta is expected value of minus d by d theta squared of log tangent. So if you plot the log likelihood curve, d by d theta squared minus is precisely what? It's curvature. At least in one dimension, you can see that. If I specialize this formula to one dimension, This is precisely the curvature of the log likelihood function, right? And it's also true in higher dimension. Not too far from it. It's a simple generalization. Once you realize how to generalize curvature in higher dimension, you'll see it's the same. Okay. Anyways, so this is what Fisher information is, and hopefully we'll see this in action. So now we have covered some basic statistics, a sort of review. See, if I wanted to explain this in all detail, I'm sorry, I will have to spend a course on it, right? Whereas we want to just get ourselves intuition, and I hope you guys know enough that you can look at what you yourself need to look. So I'm not going to spend deriving and explaining all details. But this is the thing behind it, and let's now see how it relates to what we are interested in. Okay? So if you have any questions about how the statistics shows up, you can also send me, you can ask now in the class or send me a message. So I'm going to revisit what we did last time, the policy gradient theorem. But now we are thinking this in terms of our statistical model, right? And we have a certain objective function that we want to maximize. Okay, so the objective function is essentially the value of the state, the value function for each state. This is what you want to maximize. The best policy is the policy for which the expected value of the returns is the highest. So, but we'll now look at it in our new language. Where what did it is that? Oh yeah, I have it. Okay, good. So we'll now look at it in our new language, where we want to think of our space of outcomes. Our space of outcomes is trajectories. So our space of outcomes is all possible trajectories. And if I choose a pi theta, I get a certain probability of getting a trajectory for each policy. Maybe I should write that down. So I think the slides are the original version of it. So so they are correct, but they have information in slightly more difficult order than how I finally want to do it. Okay, so our space of outcomes are the trajectories. Okay, so let's look at so typically a trajectory is what? So we'll denote a trajectory by tau, and it would start at some initial state, you take some initial action, then you move to this first state and take the first action. So say terminal state and terminal action. I mean, one doesn't have to necessarily do this for episodic case. It will turn out to be same in the other case too. But let's just consider this like that. Okay. Now fix a policy. So pi theta is fixed. So if I fix a policy, I've actually just said I have a probability of assigning an action given a state. Right? I've only said there's a probability of assigning an action given a state. How does that give me a probability of tau? So let's just call the probability, how one gets a probability on this space when we have fixed this, is there is a certain probability well, let's just start, not write a product. It's just that there is a certain probability of transitioning from S1, S0 to S1 given the action A0. So I have a probability of transitioning from S1 from S0 given A0, right? And if I was following this probability, I would have certain probability phi theta of taking the action A0 given the state S0. So this is my probability if I have fixed this policy. This is my probability for transitioning from S1 to S2 with this action. You see what I'm doing here? My probability of transitioning from S1 to S2 given this action is this product. Okay? And if I want to have all these subsequent things, so then I have to also multiply the probability of transitioning to S2 from S1 given A1 theta A1 S1 and the probability of ST from ST minus 1 AT minus 1 Okay, so the probability of getting a particular trajectory, once you fix the policy, is this product. So whenever you see in all these kind of things, in all these estimates, you don't work with the likelihood functions, you work with log likelihood functions. There is a reason for that. What's the reason? Because usually you consider independent events, and when you have independent events, the probabilities multiply. And then the multiplications become horrendous. Even computationally, multiplications become horrendous because each of these is a very small number. Each of these is a very small number. And when I compute the multiplication, even my computer might not be able to handle it, and I'll get a product equal to 0. Computationally also it's a problem. Even if I am not multiplying it, a computer is multiplying it. Multiplying lots of small numbers is a problem even for a computer. What you can do is take a log. When you take a log, actually the smaller the number, the bigger and negative the log is. And adding these numbers is not going to be a big problem. Okay? Neither for you nor for your computer. All right. So this is partly the motivation of why you will always see log likelihoods were not invented out of no reason. Anyway, so this is the probability of each trajectory. Given this is our world of outcomes, each of these outcomes has a probability. So if I wanted to look at the log of this, or there is a very simple computation. I think I have it on one of the slides. Well, I'll just show you the slide rather than write this. But anyway, so this is why fixing a policy gives you a probability measure here. And what are we looking for? We're looking for, given all sample trajectories, what is the best theta for which you will get the maximum outcome. So let's just look at it on the slide. But is this clear so far? Okay, so this thing is. Okay, I think this is why this slides are in wrong order, in my opinion. So anyway, so this is what we are interested in. We are interested in certain objective function. The objective function is what we will describe over the trajectories now. So we'll describe the reward over the trajectory. So not just say what's the reward of one state in action, but what's the reward over a whole sequence of state in actions. So I'm in the episodic case, I can take gamma equal to 1. But the calculations when you include a gamma is not difficult or different. Okay? So for simplicity, let's just not consider gamma for the time being. So you have the return for each trajectory, right? And what should be your objective function? Your objective function is to maximize the expected return over all trajectories, right? Given the policy. So the formula is more or less straightforward, which is, I think, what I have written there. But you're welcome to ask me if you have any confusion. So you have to say the probability of the trajectory times the reward on the trajectory is what is your okay, this is only defining what you are interested in. Okay? The probability of the trajectory times the reward on the trajectory is what you're going to expect to get. Right? Nothing mysterious. All right, so let's compute the gradient of this thing. Oh no. I think this is, I will have to upload another version. But it's still correct. Mathematically, it is correct. Okay, so this calculation is actually very, very straightforward. It looks horrendous the way it's typed, but it's very, very straightforward. Extremely straightforward. I'm actually worried how much have we done. I feel I'm very slow today. Oh, it's okay. And this is a standard trick. Right? So if you use this slides for taking notes, that's good. But I'm going to just kind of explain this trick. It's so standard that you should know this. And this is how also logs show up. So we have seen some reasons for logs so far, but this is another reason why log show up in all the calculations. So almost every time we are interested in some objective function, it is usually of this type. It's probability of something, okay, times the reward, or times some weight. Right? This is what the probability of getting some outcome times how good that outcome is. All right. This is your objective function. Now we want to differentiate it with the parameter. So this term does not have this term. The outcome that the reward that you get following a trajectory is constant, does not change. So all you need is to differentiate the probability of getting the trajectory depending on theta. This thing certainly changes if you change your policy. Remember, I wrote a product there. The probability of getting a trajectory depends on theta. So as you change the theta, the probability changes. So you want to differentiate that, find the gradient of that. But say this is not an expected, you would want to have some sort of a probability to get an expectation, to get an integral. So you do what you should do. So this is all tau. You multiply and divide. Every time you want to have something like that done, you want to make it into an expectation, you multiply and divide by the corresponding probability. But since you multiplied to get an expectation, you had to divide with the same thing. And this is where the second reason why log shows up in almost all these calculations. You have gradient of something divided by that. What is that thing gradient of? The log of the same thing. So what you end up having is summation over tau log So this is the expected value of this object. So I could have replaced this tau now, summation tau, and this whole thing I could replace this by some sort of an expected value of with respect to theta. Okay, so that's good. Okay, so I will do this calculation a little bit further, just a little bit further. I hope it is still here. Okay, exactly. So what is tau pt tau theta? What is the probability of getting this trajectory when we have chosen the policy pi theta? It's product of all these probabilities, right? So obviously, if I have product of probabilities, and I'm very lucky, then what we have here is a log that we are interested in taking. So before we differentiate, we want to take the log of this. Okay, so this is the thing that we want to plug in there. So what is this? By taking the log, I can convert this into sum of logs. So this is equal to gradient of sum of log of probability of going to Si plus 1 from Si given the action Ai times pi tau. This is 1 and plus log pi theta. I'm just writing that product into sums. Sometimes writing is hard. Is writing hard? Convert all the product into sums and take the gradient of that. So once I take the gradient, I can always interchange. This is not an integral. Interchanging these two things is no issue at all. So I can put the gradient inside. But this term, these probabilities of transitioning from Si to Si plus 1 given the action, they don't depend on what policy I took. This is your system. This is your environment. This is how the environment functions. Right? This is your dynamics model, if you want to use the jargon. Right? This is the dynamics model. It is independent of whatever the heck is happening, whatever heck you choose to do. So the derivative of that with theta is 0. And what are you left with? You're left with basically summation or pi the derivative of log pi theta Everybody happy so far? So what are we trying to do here? We're trying to find gradients, and we're trying to move the theta. So keep this calculation. Oh, I cannot put two ports. Okay, still okay. I think we'll manage. So what is happening underneath? You know, what is the hidden mechanism of any such gradient? What will such a gradient do? Right. So if I follow the gradient, of what I have written, so following the gradient of whatever it was, what was it? Log. This is my checker function. Okay. So when I follow the gradient here, what I want to do is make the trajectories that give me less reward less probable. The probabilities have to add up together. Make the trajectories that give me high reward more probable. So this is the whole point of moving towards an optimal. So this process will make the trajectories that give me less reward less probable, and make the trajectories that give me more reward more probable by changing the theta. Right? And what this formula says, once you've done this computation, it says, oh, all you have to do is change your theta so that my actions that give me more reward become more probable. Right? And so the overall sum of actions is the only thing that is in my control. As the wise would say, anything in your control is just your actions and not the world. So there is wisdom here. It says you can only try to improve your action. The world is not doing anything in the improvement process. Oh, wow. Come on, we talked philosophy today. Anyways, so given this is what is happening, you're improving the trajectories that give you more reward, giving them more probabilities. This is all we have done so far. Nothing spectacular. But the thing is that this thing, now that we have rewritten this can be written as expected value of sum over tau, sum over I, d theta log pi theta di si, and this multiplied by r tau. Right. So if you look at if you do this thing carefully enough, I'm not going to do this one step of calculation. So you rewrite this as sum of rewards and so on. What you will get almost immediately is what we had stated last time. So let me remind you of. So rewriting this expression here gives you. Oh, I don't know. There is another page of material. Okay, no, this is This gives you the so this is pretty much the slide from last time, I think, maybe some changes. It gives you what the policy gradient theorem states. Policy gradient theorem says that if you took even the other j that we had defined previously, its gradient is exactly given by the log likelihood of each action times the Q function. The Q function corresponds to having changed the j a little bit and adjusting this summation. So I don't want to spend time because it's also confusing when somebody else does it. You do it yourself, it's pretty clear. Okay. But even if you don't do this step, it should be by now logically accessible that that is the right gradient formula for the episode, for any other. So we have somehow linked the theory of how this thing is connected with the policy gradient theorem. And if you are only interested in very simple-minded policy improvement, then the very basic kind of approach, people sometimes call it vanilla policy gradient or whatever, is to use this theorem and say, okay, this is how the gradient is evaluated. So I discretize it, and in the discretization, I can take the Q to be given by the Monte Carlo method, and then I can change my theta according to this formula. If I change the theta by this formula, then I have basically found a way of optimizing my my whole process. So this is all this mathematics has now converged into an algorithm. Okay. All right. So before going on, there are two things. I sometimes think it depends on you. I don't mind, but is this getting 1.5 hours direct? It's a little difficult to concentrate, right? I should have thought about this earlier. But I still, even for today, I did not plan a pause for a few minutes. It doesn't have to be very big, but I suppose one has to just take it easy for a minute or two. So this is a good time, I think. It's a good time to just take it easy for a minute. And last time we have discussed how to go from here in various directions. And today I wanted to go in a very particular direction now that we have talked about this Fisher information. You can actually, there are algorithms that directly use this. Very directly use the Fisher algorithm. So the thing inside is the score function, and if you want to improve it, you can use the Fisher information. There is a direct algorithm to do that. So that is what I will talk next, but let's take a small, maybe I'll take a sip of water. So next time I will plan it in the middle. I promise. I realized this myself, that a break is kind of necessary. Even for my own concentration, because I sometimes feel that I'm losing exactly my punchlines. Okay, are we ready? All right, so I will do a brief recap. I mean, the slides are there anyhow from last time. You can see the slides from last time too. I will do a very brief recap of what the deal is going on from this very basic algorithm to something doable, workable. And the basic problem is very simple. The problem is if you do this Monte Carlo kind of thing, it's an unbiased estimate, but it has a big variance. Right? And so it turns out our whole plan to make this algorithm better comes down to reducing variance. And so we just saw what Fisher information was. For example, it's the curvature, and if it's big, then you have low variance, and if it is small, then you have high variance. So that can also somehow be useful. You can intuitively grasp that. But I'm going to revise what we did last time a little bit, maybe just the baseline way of reducing variance before we go to that. Because I think these things you forget. If you haven't seen this in between or worked out some example or something, you probably don't remember. Do you remember the advantage estimate and why it works? What is advantage? No, right? So I'm not surprised because it is something easy to forget. But it is, if you want to do these kind of algorithms, it is one of the most crucial ideas. So no point not repeating it. Repetition is always good of anything that's worth repeating. Right? Anything that's valuable. So now we know the gradient. Is the expected value of the gradient of log AS times Q bar. Have I written it correctly? I don't sometimes have I missed some term. That's right, no? So now you also don't see. I also don't see. Sometimes one has to just not have the memory after 1 hour of talking. Oh no. That looks quite okay. Okay, so I only thing that I noticed is that I should write a path. So here there is, this thing is the score function, right? And this thing also depends on pi theta. So you cannot say that this is 0 because they both depend on pi theta. But if I multiply this with something that does not depend on theta, so if I take the expected value of the theta of given as, so I know this expected value is the expected value of a score, and we just proved that this thing is 0, right? The mean of the score is with theta is 0. So I can actually multiply it with anything that does not depend on theta. So for example, I can multiply it with a base function that depends on as, but not on your policy. And this thing is still 0. Okay? So I can rewrite this gradient that I'm interested in a nicer way by subtracting this from that, and I know this is 0, so this is equal to the expected value of the gradient of log pi theta SA times Q pi theta SA minus BS. Okay? Because this is 0, we have still the same will still evaluate the same thing after expectation. There's no thing. But the point is that this something that you have added can reduce the variance in the expectation. This is the whole reason why you want to do this. So a good choice for BS, there are various people have experimented with many choices, but a good choice is the value of some fixed with respect to some fixed part. Okay, so this is saying if I compute some variance and then some value function and I subtract it, I'm probably going to get a biased estimate, but it is going to have lower variance. Okay, and this is so you could compute this using some new parameter. So you can approximate this function by a function approximator, which function approximator will use the W parameter. And you have a function approximator here anyhow, because you want to approximate the pi theta is a theta dependent function approximator. So you can represent the pi as a neural network, and you can represent this difference as maybe one or even two neural networks, depending on how you wish to do things. But there is somewhere a good reason that if you arbitrarily change theta and W, you are not going to get anywhere. So you need to have a relationship between how you change theta and how you change W. Okay? So this was one of the crucial things that we discussed last time. So you rewrite this expression and you say, okay, this will still be the honest gradient if we satisfy some conditions. And I will remind you of these conditions. We kind of also proved them last time, I remember. So where are these conditions? I suppose these are the conditions here. I want to redo this because only when I show you these conditions, it will make sense to introduce a slightly modified algorithm, which we'll see in a minute. Okay. So in this thing, you make two assumptions, and these two assumptions imply that you can actually compute the correct gradient, right? And the two assumptions is that I think we proved this last time, did we? No, I think I proved it on the board. That if you do this assumption, it's actually very straightforward proof. That's why it's not so. So basically, your assumption is that. Oh, okay. So this is only about Q, but does not matter. It will be the same for A. So although now I wanted to already start about A, but you could have the same assumptions with Q replaced by A, and it will still kind of work out, right? Because it doesn't matter. What you want is that the new object that you're multiplying here, whatever you multiply to this thing, will give you this gradient if it satisfies these conditions. And that thing that you can multiply can be A. So if I show you the proof again, you will see that it doesn't matter whether you take Q or A, which is the difference of Q with the value. This thing will still hold the true. So I can show you the proof again. It's not such a big deal. But let's just take this let's just think about this for a minute and take this for granted or maybe prove it or whatever. So what's happening is that you don't want any Q, right? You want a Q that is a good approximation for Q. In the sense that the error, so this depends on the parameter. So you should choose the parameter value that minimizes the error from the real value of Q. That is one requirement. You should choose a W so it minimizes the error with the real value. Okay, that is one issue. The second thing is when I change W now, my QW will change, right? And it should change in the same way. It should have the same gradient as the way my policy parameter changes the score function. So as long as these two vectors match, we are going in the same direction. Okay, so the proof was more or less a line, but we can look at it, okay? Because this is kind of the bit that I'm kind of worried mathematically. This is hard. One should actually not. I should stop doing slides, right? It will save me time. Because I can write this down all the time, but now when I have half thing written on the slide and half written on the board, is it? So maybe this is one of the things that I would like you guys to do. Give me a proper reinforcement learning kind of feedback. This is my first time teaching a course like this. So what I did good, positive feedback, and what I did bad, what I should not do again. Okay, so such a feedback will be very useful for me. Because I think I'm very used to teaching geometric stuff where you draw everything on the board, but now I have half my information on the slide, which I want to also use. But let's just do the board. So what we want is to minimize this error between the least square error between Q pi naught SA and your parameters value of SA. So you take the square and maybe this was an expected value, but expected value, and I take the gradient of this with that. If this is the least for all parameters, then you get this as 0, right? And then you end up getting basically saying you get 2 times Q pi naught times gradient with W of Q pi naught. Okay, so this is all an expectation. I shouldn't forget that. I can interchange the expectation and differentiation, right? Integration and differentiation. But one of the assumptions was the way this thing changes with W is the same as the score function changes. This is one of the assumptions on how you should choose your parameters. This is one of the compatibility assumptions, which was on the slide there. So if you substitute this is the score function. This thing does not depend after you have done this manipulation. You'd get that the expectation of, so you'll get E pi theta of, E or 2 times of theta pi naught SA. So this is equal to 0. So I can take this times this and say it's equal to 2 times QW as A. So, well, this time I can replace this by that, so I can just leave it here. So I can just leave this QW, LWQW. So this expectation is same as that. By just taking this times and subtracting it, putting it on the other side. But this is exactly your, so if I take the common twos away, this is exactly the gradient that you're looking for, and that is your approximate gradient as you would want. These two things are same just because of your assumption that this thing changes the same way as that, and the error is minimal. Okay, so I think this is more or less obvious, but you could have, instead of Q, you could have the advantage function in this expression, and it would still be the same answer. There will be no issue with that. Okay. So, well, I should have maybe written it like that because I want to use that for now. So this gives us now a very simple way of creating a final algorithm, which is the algorithm that I. Oh, do I have time? No. Well, okay, I'll very briefly just say what it is, and then maybe next time we'll do it. I have much more planned for today. Way more. Way more. Maybe we took a long break, huh? I hope this was useful to repeat things. So, okay, I will very briefly say how this all fits in together. So now you can say, instead of saying the gradient, which is how you will change the gradient, right? E theta is some alpha times this. So this is how you want to change things. So this is now the expected value of AWSA times something like that, right? Yeah. Okay, so it depends on another parameter. If the parameter is fixed, you can rewrite this in this form. All right. And now if you expand this, or you know that this is same as, by the assumption this is same as AW because this is our assumption. This I keep repeating. I just say these two things are the same. If you look at this and you're now saying, oh, you're taking expectation of this, you can differentiate this, you will get here as a factor the Fisher information, just like when you differentiated the score function, you got the Fisher information. Similarly, when you differentiate something like this, you'll get a Fisher information. And that you can take out and make a nicer algorithm. Okay, so that is called the natural gradient policy algorithm, or something like that. And I wanted to do that and also do some information theory related stuff like KL divergence today. But maybe we are already late. So next time I will continue here, and I hope this was useful to repeat all this stuff over again, at least somewhere. All right, so let's stop here then. Get out.